Welcome to myprojectbazaar.com.
Now we will discuss about the product for sliced message passing, high throughput overlapped decoding of high rate, low density parity check codes. Next we will see the abstract for the product. Low density parity check codes discovered were rediscovered and shown to be approach a Shannon capacity in the late of 1996. Today LDPC codes are being considered the wide variety of emerging applications such as the high density flash memory, satellite broadcasting, Wi-Fi and mobile WiMAX. Rapid performance of evaluation of LDPC codes. It's very desirable to design the better codes for the application of LDPC codes and decode its reliability of using the sum product algorithm for variation of such as the normalized min sum algorithm. Memory bandwidth is the key performance of limiting factor in the hardware realization of LDPC decoder. For example, consider the implement of LDPC code used in the NASA Landsat applications for real-time process. LDPC codes are appearing in the increasing the number of applications which have even stricter power and throughput constraints than the current state of art, requiring very good error performance. On the other hand, benefits the straightforward CMOS scaling has been slowed down the supply voltage, capacitance and the wire delay will hardly decrease the future deep submicron technology. Therefore, the individual algorithm and architecture. Sliced message passing is introduced. The key idea is to slice the total number of variable check message and is equal to the equal sized chunks, then to perform the check node computation sequential chunk by chunk. The hardware architecture of SMP decoding is introduced. Each check node processing unit is proposed to the register based parallel architecture as only the input interested as the inputs. An optimized SMP decoder has been further implemented for a 2048-bit LDPC decoder of the emerging of IEEE 10G base T standard in IBM CMOS 90 nanometer process. A synthesis tool of QZ is described by the which takes the matrix of Q's cyclic LDPC codes of resource characters of FPGA and automatically senses the vector or folded architecture that maximize the decoding throughput for the codes of the given FPGA process. Next we will see the flow diagram for the product. First of all, register based partial parallel architecture. As a fully parallel architecture will cause the high hardware implement complexity problem, while the memory sharing partial product architecture is limited by fragmentized memory units of high throughput application. The trade-off between the hardware cost and throughput is achieved by the register based parallel architecture. The temporary results are stored in the register rather than the memories and multiplexers to control the interconnecting wires. SMP decoding block. Each CNU has 8 input messages. Since the shift register, deregister are used to data buffers, then they are reallocated the right after the BLUTs to store the transformed input data. T register here are used to store the update the data accumulated in every clock cycle. The 32-bit multiplexer serves as the data latch to keep the output data unchanged during the decoding iterations. Optimized CNU SMP decoding architecture. The CNU of SMP decoder as the input. It can observe that the hardware advantage of the SMP decoder will be diminished if it is row weight small that the parallel factor is large, to such throughput as several hundred megabits per second at the low data rate. Because the throughput is not most critical issue and the large number of rows and columns can share on the CNU architecture. optimized in the multiplexer RLUT SM2 2's complemental block in CNU architecture are now moved inside the VNU, and the 2's complemental block are moved to the CNU because the number of VNU is scaled by the parallel factor. Moving the block of the CNU into VNU can save the overall hardware cost. Hardware optimization process. The rebalanced architecture of VNU and CNU was constructed. They calculated the critical path done which the smallest VNU and CNU leads a high frequency clocking pulses. Moving the CNU and VNU save the hardware cost. The VNU CNU updating the stage of critical path constraint and evaluator process. Finally, we see the output for VNU and CNU sliced message passing decoding architectures. Just we run the Xilinx ISC project. This project is developed by the Verilog languages. The CNU and VNU process is separately considered. First of all, the VNU process is to be selected simulation process. Then select the simulate behavior model. They run successfully. Then it open the ISM project navigator. We apply the binary input data to display the decoding result for ISM project. Any of the 8-bit data to be applied for decoding result. Then to apply the full clock cycles, just we change the selection line process. Then apply the clock cycles. You get the decoding result for our CNU based SMP architecture. Then close the simulation result and implement the VNU architecture. Then to select the RTL schematic diagram for the VNU architecture. Then to run the VNU synthesis result and VNU RTL schematic diagrammatic representation. add and create the CNU RTL schematic diagram, VNU RTL schematic diagram, then technological diagram, then the technology diagram for VNU architecture, then the design summary to apply the synthesis report for VNU structures. The VNU structures consider the more number of register elements, so the area to be increased the VNU architecture, and the timing allocation, delay time and the latency to be calculated the more compared to the CNU based VNU architecture. Then the same procedure for CNU architecture to compare the area and time allocation. This is the less compared to the VNU results.